How about now?
Yeah, now we can see that it's starting.
Okay.
Yeah, we can see your screen.
Okay. So I'm going to read the question. Give 3 key characteristics of wave equation. So first of all, we know waves are means of transporting energy and information. The three characteristics of waves is they travel at a constant velocity, they radiate outwards from a source, and they assume properties of waves. So the properties of waves are frequency, amplitude, wavelength, speed. You know those basic formulas. So that's it for the first part. Second part is explain the term intrinsic impedance for good conductors. So intrinsic impedance, I hope everyone can see my presentation.
Yes, tunaiona.
Oh, okay. Awesome. So intrinsic impedance is that impedance of a medium. In this case, we're talking about good conductors in which wave is traveling. So hiyo resistance unapata kwa hiyo conductor when wave is traveling is that what we call the intrinsic impedance. So this is the formula here. N is equals to the square root of J omega mu over sigma plus J omega E. So this formula is gotten from once you equate the four formulas for Maxwell equation. That one you can find in page 350, but I'll just start from this formula. So we know for good conductors, conductivity is much, much greater than omega E. With that being said, N will be J omega mu over conductivity. So that's the first formula for intrinsic impedance. To find the absolute, it's the square root of omega mu over conductivity. Now, when you're talking about intrinsic impedance for good conductors, we can either represent it as in equation 2, or we can put in this type of equation, in that intrinsic impedance is equals to the absolute intrinsic and its phase angle. We know intrinsic impedance has nearly equal real and imaginary parts. Therefore, its phase angle is approximately 45 degrees. That's why you can see here we are putting 45 degrees. So I hope you note the 2 formulas, or rather the 4 formulas for the intrinsic impedance. Now, in case we're talking about lossless medium, the conductivity is equals to 0. So the formula changes. If you remember, the initial formula was square root over J omega mu over conductivity plus J omega E. So when conductivity is equals to 0, once you do this calculation here, you'll get intrinsic impedance for lossless medium is equals to the square root of permeability over permittivity. Now, when when you break it down, it will be mu naught mu r over E naught ER. Now when relative permittivity is equals to 1 and relative permeability is equals to 1, you will realize when you do this formula and input the values, you will get it to be 120 pi or 377 ohms. So what is skin depth and skin effect? So skin depth is the measure of depth in which an electromagnetic wave can penetrate the medium. So I'll give you I'll explain using an illustration. So when waves enter into a conductor, as you can see here, as wave enters into this conductor, the wave suddenly attenuates. It starts reducing gradually, as you can see. So that reduction by a certain percent or by a certain factor is what we call skin depth. Now in this case, as you can see, the reduction is by a factor of 1 over E the reduction is by a factor of 1 over E. So let's go back and do the calculation. I hope you've understood this part. Let's go and do some few. Okay. So I want to find the formula for skin depth. So we'll start with just the basic wave equation. This is the basic wave equation. So E naught, okay, we know E is the permittivity. Now E naught is the initial amplitude. So this is the initial amplitude, like that, E naught. So yeah, it's propagating along the Z axis, and the variation is along the X axis. You remember for the intrinsic impedance for good conductors has a phase angle of 45 degrees. So if we put 45 degrees here, it will look something like this. So it's propagating with a phase angle of 45 degrees. I hope now we have like some visual representation of what I'm doing. So back. So if the initial amplitude goes down with a factor of 1 over E, you get E naught, E into power sigma and then the skin depth. So you will equate these two. We can see E naught and E naught is here, so you cancel it off, and then the powers you will equate the powers, which will be this is actually attenuation. Sorry, attenuation. Skin depth is equals to 1. Skin depth is equals to 1 over attenuation. While using the formulas for Maxwell equation, you will get to find this formula. So attenuation is equals to magnetic field intensity, which is equals to square root of pi f mu conductivity. So you will replace this formula here, and this is the skin the skin depth. So another definition of skin depth is the distance through which the wave amplitude decreases by a factor of 1 over E. Yeah, I hope everyone has understood that. Let's go to skin effect. Skin effect is that phenomena whereby the field intensity in a conductor rapidly decreases. Well, we have already understood what skin depth is. So that's, how do I say it? That's that feeling, quote unquote feeling, whereby the field intensity is decreasing rapidly is what we call the skin effect. Elaborate why the skin depth is important in EM shield. Okay. So first and foremost, I would like to.
Situna, I have a question.
Yeah.
Back to skin effect.
Yeah.
Let me see, phenomenon whereby field intensity in a conductor rapidly decreases.
Yeah.
Oh, so there are two skin effects.
No.
If I'm getting this right, there's where we find skin effect in ECT, and then the skin effect in EMF. Am I getting that right?
Elaborate, Joseph. Elaborate your skin effect ECT.
Whereby at high frequencies, charges tend to flow on the periphery of the conductor. So that's why they are usually hollow and stuff.
Actually, it's the same.
It's actually the same.
The same meaning. Okay, let me elaborate further on the skin effect. So we know that skin depth is gotten from the reason why we have attenuations, because it's there is AC wavelength, there's AC.
Mm-hmm.
So will you give me like a few more slides? You finish this slide and then I'll explain.
That's okay. That's okay. Yeah.
Okay, thanks. So back to the question, elaborate why skin depth is important in EM shielding. Electromagnetic shielding basically is reducing that electromagnetic field in space by blocking the field with barriers made of conductive or magnetic materials. This can be, an example is for an example of EM shielding is the one that we use in our phones. For example, I call, okay, where I live, we have an airstrip just like 40 meters away from our home. So like today, when I called Nigel, there was some static in between our phone conversation. So that immediately hit me that there was a helicopter that was passing nearby. So, you know, this for planes or these objects that affect your that cause those barriers affect the communication. So that's one of an application of an EM shield. I hope you have understood. I hope that is clear. Yeah. So as I was saying, electromagnetic shielding is the practice of reducing that EM field in space by blocking it with a magnetic material or conductive material. Let me show you an example of. You see, in our phones, you have like this type of shield cages. they are used for EM shielding. I hope you have understood. So skin depth is also defined as the depth where current density is just 1/E of the value of the surface. So skin depth is important for EM shields because conducting shields must be thicker than the skin depth to reduce interference from other EMF. So I can let's go to the next question. Due to propagation in good conductors, explain the phenomena that occurs in terms of resistance and effective area of the conductor and frequency. What is the remedy? Yeah, as I was saying about AC, I was saying skin effect is the tendency of an AC to become distributed within a conductor such that the current density is largest near the surface of the conductor. That's what essentially Jose, you are asking. It's the same thing. So current density, it's largest near the surface. Hapo katikati, it's very little. It's very little. So we realize that it decreases exponentially with greater depth in the conductor. So just have I explained, have you understood what I have explained? Have you gotten it? Joseph? Okay. Yeah? What's for you? Okay, so skin effect reduces effective cross-section of the conduction and increases effective resistance. So because using large full conductors, completely full conductors will be a waste. It's recommended that you use tubular conductors such as pipe to save cost and weight, because as we have realized, skin effect only covers the area that is near the surface of the conductor. Hapo katikati is almost next to nothing. So another way you can solve this is by using braided wires with many fine strands, and this is mostly used in high frequency. So skin effect will have little effect on each of the thin strands. The bundle does not suffer the same increase in AC resistance that a solid conductor of the same cross-section area will do to the skin effect. So basically that solid conductor will not, like, it will be a waste if you use solid conductors. So it's recommended you either use tubular conductors or braided wires. Let me show you some pictures of how they look so that you can have some visual presentation. So this one is a braided wire. You can see they have like mini wires. So they have mini strands, they have thin strands, and the skin effect will be very little. Oh, I thought I had another picture, but yeah. So that's the end of my presentation. Any question? Okay. Thank you. I'm done.
Thank you, Situne. And thank
Yeah,
you to you and Nigel for, oops, yes.
It's okay. I just want to add something about electromagnetic shielding. Like in real life applications, it's being used in devices that propagate waves, gamma microwaves. So I just want to advise guys, like mkimada kole, like I know right now kila mtu anaishi kwa nyumba ya parents wake, but of course after a few years you'll get your own place. Sasa kununua microwave. There's some microwaves, okay, generally microwaves zinakuanga na protective layer, protective sheet around it. So like it helps with electromagnetic shielding such that it reduces the impact of the waves. But now waves zingine hutoka nje. Lakini of course manufacturer atakwambia hizo waves zenyewe haziwezi kuaffect in any way. But the truth is now ukibuy a the waves they pass through the shielding on the door. Okay, sometimes it may take like 2 years, then it becomes weaker. So to be on the safe side, just changa some money, alafu buy a good microwave, because in the long run it will help. Buy a cheap microwave and you just might get cancer. So just advice, yeah. Okay, tunaweza endelea Nyakami.
Thank you so much. Nilikuwa tunawaambia asante. So that's all.
Okay, can you guys hear me?
Yes.
Yes.
Kidogo. I'm presenting with my phone, so just give me a few. Okay, watch broadcast. Okay. Oh, okay. Can you? Oh, okay, good. So, kidogo. Haya. There is. Can you guys see well? I was doing question 1 to 4. I don't know if you can see well. I don't think you can. Oh, you can. So, question 1 says, in principle, state the difference in magnetostatics, electrostatics, and time-varying electromagnetic fields. Relate the 3 fields with expressions of the electric charge. Could you go back? Question 1 was here. Okay. So, okay. So, magnetostatics, the static fields are produced due to motion of electric charges with direct currents or static magnetic charges, while electrostatic fields are produced when charges and currents are stationary and do not vary with time, while time-varying electromagnetic fields are produced due to time-varying currents, which is, in short, magnetostatics has requires steady currents, electrostatics has static charges, and time-varying has dynamic currents. So that's that. Yeah. Then that's called what? The expressions of the electric charges are here. Okay. Because the first one has steady magnetostatics has steady current, but its charge changes with is time varying, so it's dq over dt is equals to I. Then electrostatics has static charges and its It's saying its currents and charges are stationary and do not change with time. So it's just Q. And then time varying is both the current and the charges change with time. It's time varying. Yes. Then number 2 was, it is so difficult. Number 2 was state the Lenz's law of electromagnetic induction and deduce Lenz's law. Then you give 2 types of examples of the sources that produce electric fields. That's number 2. So Faraday's law states that induced EMF in any closed circuit is equal to the time rate of change of the magnetic flux linkage by the circuit, which is, in short, VEMF is equals to d psi over dt. What's this psi over? This thing, I don't know how to call it. The one that stands for someone. Well, anyway, so Lenz's law states that induced voltage acts in a way to oppose the flux producing it. That's why it comes to, oh, it's psi. Sorry, psi is this other one done for n, which will become negative n d psi over t dt. That's why the negative is there. So that incorporates Lenz's law into Faraday's law. Yeah. That's weird. This one, I'm using my phone. This upside down Y is the flux leakages. Yes. The sources that produce electric fields are batteries, fuel cells, and generators. Yeah. No. Number 3 was done with me and Danson. So I'll go to number 3. Go back. Ole, done. Sorry, my phone is refusing to cooperate with me. Done. Yes. So number 3, I'm going to load shortly. Number 3 asks, it's what's going on? Can anyone see my screen?
Oh, we stopped seeing your
Oh my
screen.
God. Whoever's going to do number 6, please go on. So I mean, my laptop had refused to download anything. Let me try again and then use my laptop because my phone is also being difficult. Very sorry.
Haina shida. Sawa sawa. I think I was the one who's to do number 6, yes?
Yeah, I think so.
All right. Let me start the presentation. You guys can see my stuff?
Yeah.
Okay. Okay. Wait, sorry, you mixed up some stuff. I need to find it. So the problem of question 6, sorry, was this one. It was long, but it was telling us that to write down the vector equations for Poynting's vector and explain what the symbols used mean. And then they also asked us to tell the significance of the 3 parts of the equation, then the state, Poynting's theorem, and how is net power determined from the vector. There are so many things this question was telling us to do. And then there was the calculation question. So the first theory parts are mostly in our notes. The statement for Poynting's vector is that the net power flowing out of a given volume V is equal to the time rate of decrease in energy stored within the volume minus the conduction losses. I think this kind of makes sense in a way because they're telling us that the net power flowing out is the same as the rate of decrease in energy. Like it makes sense because power we know is rate of like energy over time. So we know it's going to be a rate of energy doing something. So I think that's why it makes sense that it's a rate of decrease in stored energy within a given volume minus the conduction losses. Okay. The next thing is the Poynting's vector. Poynting's vector looks like this. The Poynting's equation, sorry, is this one, where the P stands for Poynting's vector, the E stands for electric field, and the H is magnetic field intensity. Yeah, and those are just the 3 parts. You just curl them. E curl H. That's it. That's Poynting's vector. Like basically Poynting's vector helps us when we're getting the energy. Yeah, it helps us to be calculating energy in a nice, smooth, quick way. Like if you think maybe the other way of calculating energy might have been to get an equation with attenuation of energy, and then you use that attenuation in a way to calculate. But that's not what Poynting's vector tells us. Poynting's vector just tells us to just curl them, then this gives us a rate of change. Then the last part is telling us that, what is the significance? Okay, we'll get to that. How is net power determined from the vector? So, Poynting's vector gives us a rate at which energy is leaving a given volume. Yeah, so if we want to get the total energy leaving a given volume, we have to do the surface integral. Integrate with respect to the surface. Wait, I think I had a better way of saying that. Basically, if this is your, wait, are you guys seeing the one note?
Yes. Yes.
Oh, so if this is your thing where there's energy inside, in order to get the, let's say you have some current coming like this, in order to get the total energy, you'll integrate Poynting's vector over this surface, over the surface that where energy is leaving. So maybe it might be all 3 surfaces or just one or something like that. Yeah, that's basically what we do with the Poynting. Yeah, and then now the last part is the significance. Not sure exactly how we are supposed to answer questions asking what is the significance, but I thought that maybe the significance would be explaining how the explaining how to get the net energy and also explaining the meaning of electric field and magnetic field intensity. Yeah? Okay, so maybe let's go to the calculation part. Wait, does anybody have a question? Oh, Celestine, you have a question?
Bill,
Yeah?
could you able go back to your that PDF presentation? The type yeah, able shuka chini
Not
to the part where you say
spoiler.
the surface.
Sorry for
Oh,
the
okay.
spoilers. We're coming down slowly.
Okay.
Yeah. Anyway,
The
let's
part,
go to the part where
the part where you're talking about surface
surface
integral.
integral. Yeah,
Yeah.
we'll get to that. I think with a question,
Okay.
easier to
So,
explain that surface integral thing.
so no
Or
problem.
rather, with this question, it was easy to explain the surface integral thing.
Okay. So,
Anyway, let's continue. So now, this, how is net power? Oh, this one, a straight Y is oriented along the Z axis and a current I is flowing through it. Use Poynting's vector to determine the total power. Okay, so this one looks something like this. I had tried to draw it. Let me draw it better. This is our Z axis, and then we have a wire. Now, on that wire, there's a current I. Yeah, current I is flowing through that wire. And then they want us to get the rate at which power, the total power entering per unit length of the wire, the total power entering per unit length of the wire. So the steps for this are pretty, what's it called? The steps are simple because Poynting's vector, as you can see, is not very long. It's just 3 terms. The first term is Poynting's vector itself. The second term is electric field. And then the third term is magnetic field intensity. So step 1 is to get electric field. Then step 2 to get magnetic field, and then you cross them. I did it in reverse. I crossed them, then I got magnetic field, and then I got electric field. So the magnetic field, that's it called, the magnetic field intensity. Okay, for a long wire, I think this is maybe an explanation point. If you recall, there are those long equations which we usually hope he doesn't tell us to derive. He even said during a lesson that he usually sees those ones as postgraduate. But the concept is that for a long wire, if you want to get the H, if you want to get H for a long wire, the equation is this one, is I over 2 pi rho naught in the A phi direction. Let me explain what that means. If you remember what's it called, the right hand grip rule, if you are to do a right hand grip and then this is our wire going in the Z direction, you'll find that your H, because I is going up, so H has to come something like this. Yeah? You all remember that from right hand grip, I hope? Yeah, I think we all remember. We have memories. So from right hand grip, you do that, and then you get I. This is the current flowing in the, this gives us the direction of H. So as you can see, H is going like that. Yeah, so that's why the direction of H is in the A phi direction. Okay, maybe I can explain the A phi. Like here we are using the cylindrical coordinates. So in cylindrical coordinates, there is rho. Oops, sorry. There is rho, and then there is phi, and then there is Z. Now, since we've been told that this wire is in the Z axis, it means that the two axes remaining are the rho and the phi axis. Now the phi axis usually goes round because it's an angle. Yeah, so we are going round. That's the phi axis. And then the rho axis, that one goes outwards. Hope that's making sense to people. Yeah, so the rho axis goes outwards and then the phi axis goes round. If we were, actually, I don't know what I want to say. But there is the equation which I hope you guys, like you can go through the derivation of this equation. It's in Minakumari, the beginning of Biotsavat, that place where they're talking about Biotsavat. Are you understanding what I'm talking about? Let me check.
Yes.
Oh, so yeah, there was a question, a confusion point. This one, why are we using for an infinite line, yet they are asking per meter? Like this equation, I over 2 pi rho, I over 2 pi rho gives us the h for a infinite line. But then for a finite line, it's usually something like I over 4 pi rho times some cosines. You do something with cosines. I think it's cos alpha 1 plus cos alpha 2. And then now when it becomes an infinite line, that cos alpha 1 plus cos alpha 2, it becomes 0, cos 0 plus cos 0, which is 2. And then 2 and 2 cancel, and then it becomes this one, I over 2 pi rho in the Fi direction. So, like my question is, since the question is telling us terming the total power per unit length, why then are we going to be using the formula for infinite line? Maybe who can try to answer? Okay. Nobody is trying to answer. Okay, maybe I can explain to save on time. The reason is that you see for the what's it called? We're calculating power being lost per meter, but power at any given point is dependent on the whole, but H at any given point will be caused by the whole line. Like the power, yes, we are calculating power for this section only, but H for this section is caused by the whole line. So that's why we use the formula for the infinite line. I hope that's clear. Okay, I hope it's clear. The next step is to get the current, or rather now if you're coming now, this is now the first step, yeah? We are looking to get the electric field. Yeah, because that's the first step in getting Poynting's vector. So in order to get the electric field, we use this formula. This is what we call Ohm's law. Ohm's law in point form, yeah? J is equals to, sorry. Where am I? Yeah, that's a question, Amma. Oh yeah, let me repeat that thing for where we're using for infinite line. Like I'm saying that H at this point, yes, we want to calculate the power being lost in this section only. But H at this point is not only dependent on the H for this section only. H at this point is going to be caused by the whole wire. Yeah, it's not only being caused by this. The H is being caused by the current in the whole wire. So that's why. Is that making sense? Like yes, the power which we are interested in is only this power, but this power is dependent on this H. And this H is caused by the whole line, not just one point. Hope that makes sense. Yeah, okay, that's better. Okay, so now the next, yeah, we want to, this Ohm's law in point form, yeah, J is equals to sigma E, and then it's not a lot of calculation. Yeah, you just put sigma down here, divide both sides by sigma. Now it becomes very straightforward. Now, J is current density. So current divided by area. And what's our area? Pi r squared. This rho naught is the radius of the wire. So pi r squared. So I divided by pi r squared, that gives us the J. Then you divide that by sigma. And that's it. That's how it works straight. There's no story to it. That's why you should have started with it instead of starting with the H. Yeah, so now we have E and H. Now we go to step 3, which was actually step 1, which was not step 1. This is actually the ending of part 1, season 1, section 1 of the solution. That like getting the P, the pointing vector. So now if you can see, E is in the Z direction and H is in the phi, phi direction. So now it means that the pointing vector, since it's the cross of the two, is going to be in the rho direction. You can remind yourself that it's in the beginning of our notes for last semester. And then you just you do the cross of the two. So now it's going to be magnitude of one times magnitude of other times sine of the angle between them. And phi and z are at 90 degrees to each other. So it's just this times this in the rho direction. Just straightforward, you just multiply them one time. Okay, so now the next part, which is the second part, is to calculate the total power. And in fact, this is the last part. So now this is where the area thing comes in. Like, if you think about it, this wire is like a cylinder, yeah? And then current is flowing like this, yeah? But then power is being lost like this. It's being lost outwards. Why is power being lost outwards? One thing is you can't say power is being lost by the top surface and the bottom surface. Why? Because that's the direction where current is flowing. It's not like it's open to the outside of the outside world. So power isn't being lost through those surfaces going outwards. Power is only being lost outwards in this direction, in this outer direction, yeah? So the area that's responsible for our losing of power is this area here, which we used to call the curved surface of the cylinder, yeah? So that's why, that's the area which we're going to use in calculating the power, in calculating the total power loss, yeah? So it's just, you do the surface integral, and then you just bring Poynting's vector inside straight. And then you do the surface integral. Maybe there's something I can add. Oh, don't mind about these symbols. They're just, you're just meant to do the surface integral. Like, the Poynting vector is giving for a small area. So now you want for the whole 1 meter. So now that's why we're doing the surface integral. And then it looks something like that. Our limits are from, phi is going from 0 to 2 pi, and z, is it z? Yeah, z. For z is going from 0 to 1, or L. I used L because I was copying Mina Kumari. Anyway, and then you do the integration, yeah? The good thing about this integral is that it's so easy. Everything is independent of the bounds. So you can just bring this I squared over A, I squared, sorry, is pi supposed to be squared? Sorry. Yeah, you can bring I squared over this outside, and then you integrate from 0 to 2 pi, and then from z to, it's from z going from 0 to L, yeah? And then when you do that integral, you're going to end up here. I squared L over A sigma. Why is that? Okay, maybe I should have added the integration. Like, if you bring this outside, you're going to be left with we're going to be left with integral from 0 to L, and then integral from 0 to 2 pi of d phi dz. And then when you do the first integral, you're going to get it's just 2 pi. So now our integral becomes 2 pi times the integral from 0 to L of dz. And then here, this one is just going to become L. So it's going to become 2 pi L, and then we're multiplying by this. So that's where the 2 pi goes. Then we're going to be left with pi r squared times sigma. And pi r squared is just the area. So now it's I squared L over A sigma. Now, if you have some memory, you'll remember that L over A sigma is actually the formula for resistance, because sigma is actually 1 over resistivity. We are going to have L rho over A, rho L over A, and that's the formula for resistance. So actually, this whole process, it's like we've derived the formula I squared R. And yeah, that's it. If you want to go through it, it's in Minakumari, page 391. Just the problem 6. Any questions? Okay, thank you.
Bill, would you be so kind to send the document you're using over to the group?
Okay, wait, Alvin has asked a question. Let me answer that question. And then, yeah, I'll send it. I think sending is easy.
Thank you.
Wait, she's asking, please explain how ds is equals to rho d phi dz. Okay, that one I can explain. Rho d phi dz, yeah? Wait, where's my mouse? No, I think a new section for that is okay. So this here, think of a cylinder, yeah? And then this is our z direction. Yeah, and then our phi direction is going like this. And then our rho direction is going outwards. Yeah, so if you think about a small area in this curved surface, let's remove this and then we bring it out. It's going to look like something like a rectangle like this. Its height is a small change in z, so that's dz. And then its length, no, we call that one width. Sorry, is it height? Length, width, height. Its length, its width is dz. This is the width I'm talking about here. And then its length, what? English. Its length is some arc. Like, think of connecting this to the z-axis. It's going to be some arc length, yeah? This arc length is going to have a length of theta. How we used to say it is theta over 360. Theta over 360, something like 2 pi r or something like that. Yeah, it used to be something like that we used to do in high school or in primary. Anyway, and then after this, we move on to the new unit. This is degrees. We don't do degrees anymore. We move on to radians. Yeah, so in radians is going to be theta over 2 pi times 2 pi, and our R is actually rho. It's not going to be d rho because rho isn't changing here. Rho is a constant value for this arc. Yeah, for this arc, rho is a constant value. So it's going to be times rho. And our angle now doesn't have to be theta. It's actually what we're calling d phi, a small change in the angle. So here we're going to have phi rho. So rho times phi, d times d phi, sorry. So now the small area is rho d phi dz. Hope that answers the question. Oh yeah. Any other question? Oh, the sharing. Yeah, I'll share just as soon as I'm done presenting. Any other question? Okay, no questions. So, thank you.
Thank you, Bill. Mesh, are you ready to present?
Yes, I am.
Okay, so
Can everyone see my screen? Okay.
Yes.
Alright, so, where's number one? Here. Then question 1 to question 4. So question 1, the difference between magnetostatics, electrostatics, and time-varying electromagnetic fields. So here it is. There's my notes. Sort of electrostatics are due to static electric charges, which is Q. Then magnetostatic fields are due to motion of electric charges with uniform velocity. So the relationship will be I is equals to dq over dt. And then the time varying fields are due to accelerated charges. Yeah, it will be the squared. You'll differentiate I second time. Yeah, you differentiate I, so it comes to di over dt is equals to d squared over dt squared. Yeah. Then number 2, state Faraday's law and deduce Lenz's law and give types of electric examples of the sources that produce the electric field. That one is here. So Faraday's law states that induced EMF in any closed circuit is equal to the time rate of change of the magnetic flux linkage by the circuit. And then Lenz's law states induced voltage acts in a way as to oppose the flux producing it. So VEMF is equals to I still don't know how to say this one, but it says flux linkages over dt is equals to negative d phi over dt. Anyway, then the sources that produce electric fields are batteries, fuel cells, and generators. Then number 3, we'll first go through this. We'll go through how to essentially. Okay, number 3 was about consider a moving loop in a static B field. A straight conductor moves perpendicularly to its axis in a uniform B field where the flux density is given as 3 Tesla. If the velocity is 24 meters per second, evaluate the electromotive force induced in the conductor if the direction of motion is an angle of 30 degrees to the orientation of the field. What is the direction? What is the orientation that will result in no EMF? Explain. Now, first, we'll go through this. Yeah. So, the variation of flux may occur as follows: having a stationary loop, which is also known as transformer EMF. time varying loop in a stationary B field, which is motional EMF, and hybrid EMF, which is a mixture of the transformer and the motional EMF. So in case 1, we'll have V EMF is equals to the circular line integral of E dot dl, which is the surface integral negative of the partial derivative of flux density times yes. So applying Stokes theorem. So Stokes theorem, we had it in past time in math, which stated, if S is an open two-sided surface bounded by closed non-intersecting closed surface, then if A has continuous derivatives, then essentially this, ADR, which is EDL in this case, EDL will be equal to the surface integral of, EDL will be the same as the curl of E multiplied by the derivative, a small change in S. Yes. So the line here equals to this. Yes. Then this end means, so it ends up being, it's gonna be the curl of E is equal to negative D. Sorry. The partial derivative of the flux density. Yes. Then the curl of E is not equals to 0, meaning that the time varying field is not conservative. Then the second one was the moving loop in a static B field. So this F is equals to QUB. I'll send a YouTube video where he explains this, like just generally the Maxwell's EMF and how this came up in depth. Yes. So F is equals to QUB. This should not be mu. I'm sorry, it should be U. U, which is velocity. Yeah. If the charge velocity cross the flux density. So the motional EMF is given by F is equal, usually it's really F is equals to QE. So E, so to the formula, it becomes F over Q. And then since F is QU cross B, the Q's will cancel, we remain with U cross B. So the induced EMF becomes, you replace this E over here, becomes U cross B times small change in L. So if the conductor is of length L, this becomes UBL. And then if there is a change in, usually it's perpendicular to the magnetic field, meaning that's 90 degrees. So when you do UBL sine 90, 90 is 1, sine 90 is 1, so it becomes UBL. But not if there's a theta. At theta, it changes. Then another thing to note is the smaller the value of this one here, the theta, the lower the induced EMF. Yes. Then we did a question. Okay. This question is the same as same as this example, option 3 here. No, where did I? Okay. Upload. Okay. So let me just write it down then. Okay. Nitaandika hapa juu. So this is our L. This is our V. This one, or rather, sorry, it's our U. Okay. Then this is our B. Yeah. So normal to the field. Question 1 was, normal to the field will be at 90 degrees. Sorry. Then parallel will be at 0 degrees, and then this one is 45. So normal to the field, remember our equation is V EMF, our induced EMF, which is equals to U of velocity, V our flux density, L our length, then sine theta. Okay, so when you input this here, you get U is 40, V, you change this into meters, to be 0.3 meters, and then sine theta, which will have our theta as 90. So when you calculate it, your answer you get here as 12.24 volts. And parallel to the field is the same thing, but theta now will change to become 0 degrees, and sine 0 is 0, so it will be 0. And at an angle 45 to the orientation of the field will be input 45 here, you get 8.65. So as you can see, when 45 got, like 45 is smaller than 90, so as it got lower, the induced EMF got lower. Also, just on page 563. Oh my god. Acha tu, hiyo sitaipata saizi. Haya, then about question 3. Oh yes. So now when you're doing this, our answer is yes. So we did theta is equal to 30 VUBL sin theta. Our V was, our velocity was 24, our U was 24, to 24. Our U was 24, our B was here, 3 Tesla, our length was 2 centimeters, which is 0.2 meters, and our theta was 30, so you get 7.2 volts. Then, what is the orientation that will result in no EMF? So if the conductor was to be placed parallel to the field where the theta will be 0, then the induced EMF will be 0 as there is no flux linkage. Yes, that's number 3. Then number 4 asked us about the explain Maxwell's equations for time-varying electromagnetic fields in integral form and explain their physical significance. Okay, now okay, first Maxwell's equations look like this. This is the differential form. Then in the middle, that's where we have the integral form. So, yeah, the physical significance of Maxwell's equation. I know here it's in the differential form, but now you put here the integral form. Then the differential form of the Maxwell's equation is useful in calculating the magnitude and electric field at a single point in space. But then the integral form, it finds it over an entire region. So like, say, because you get, yeah. So the first one, which is this one, the Gauss's law of electrostatics, it is time independent. It is time independent. The electric flux flowing through any closed surface is equal to the net charge enclosed inside the surface divided by permittivity of vacuum, which is, okay, hapo amestate the Gauss's law of electrostatics. Yes. And then the second one is the integral of the flux density multiplied by the small change mass is which is independent of time, when the magnetic field B has a divergence equal to 0, the magnetic monopoles cannot exist. Because in here, like the first equation is the electrostatics is one we did in, it's called what? In first year, I think. The one where you have a charge, the charge can, two different charges, they can influence each other and all. But then this one, okay, some YouTuber was saying how the divergence are usually for at a point. They are for this is for a point, and then the so now like to get magnetic field, they exist with not like things as a pair. You can't just find like in charge there's just this one here, a positive here that's going to return into it's called what? Going to radiate away from it charges and all. Now here we can't have just north, it has to be north and south. So the second Maxwell's equation just essentially just boils down to this. Yes. Then the third one is Faraday's law, which we handled earlier. Yes. Then it relates the space variation of E with time variation of B. So it relates B. This is where now B and E come together. We see how the electric field is able to influence the magnetic field and vice. Yeah. So it relates with this space variation of E with time variation of B. Time variation of magnetic field induces an electromotive force. Faraday's law of induction and the negative sign justifies Lenz's law. We handled this in the previous question. Yes. Then the fourth equation, this one is Ampere's circuital law, which states, the Ampere's circuital law first, it shows relationship between the current and the magnetic field. So, the time-dependent equation, first of all, and then it relates magnetic vector with the electric displacement vector and current density vector. Magnetic field is produced due to the combined effect of conduction current and displacement current density. It is the modified differential form of Ampere's circuital law. Then Ampere's circuital law generally states that the integral of magnetic field density B along an imaginary closed path is equal to the product of the current of the enclosed current by the path. What? Is equal to the product of the current enclosed by the path and the permeability of the medium. So Ampere's circuital law, this one, is that the this is mu O. Then this is I. Yes, that's Ampere's circuital law. That's what it states. Yes, that's A. Now B, from Maxwell's two-colour equations for free space, obtain a 3D wave equation both in E and H field, hence show that the velocity in free space is given as 3 times 10 to the power 8. Yes, here it is. So let a region of free space be free of charges for which mu and E are constant. So modify Maxwell's equations as follows. So the divergence of B is equals to the first Maxwell's and the second Maxwell's are equals to 0. First Maxwell's equation, second Maxwell's equations are equals to 0. Then now we're going to deal with the curl of the equation. So I'm looking for my pencil. So the curl of E is equals to negative B. The change in B over dt is equals to this, and then B is equals to permittivity times the H, which is magnetic field intensity. So then the fourth equation, equation 3, and then equation 4, and then D is really equals to E. This is capital E, and that's epsilon. So that's why it becomes. Oh yeah. Then in free space, in this state, J is equals to 0. So we're only going to deal with the what do you call it? JD, which is the displacement current density. Yes, this displacement current density. So we're going to take a curl on both sides on the first side of the, we'll begin with, in our question, we'll start with getting H first. H first. So we'll take a curl, H, the equation for H is this one, equation 4. So we'll take a curl on both sides. So the curl of H is equals to the epsilon and this part. And remember this. So this was like when you open, not when you open it, but this is equals to this. Then remember from up here we said when you're modifying, this one is equals to 0. So here this one will go to 0. And we're going to minus the squared of H is equals to, then you have this. So this comes out, then you back with this and this. So that brings us to, comes down here. So negative this is equals to, we're going to replace this one with number 3, which is negative mu over dH over dt. So here it is, negative mu. So then the constants, which are mu and E, come outside, and then the rest, come here. The negatives go away. It remains this part and this part, which is our wave equation. Then for freeze, okay. Yes. So now to get the 3D wave equation, we're going to make this the subject of the formula. So this comes here, then this comes here. So it becomes d squared H over dt is equals to the partial derivative of H is equals to the squared is equals to 1 over mu E. We're going to divide here by mu E multiplied by 1 over mu E. Then del squared H. Then that okay, let's just go. Then you end up having this one is, then U is the velocity. Velocity is equals to the square root of 1 over mu E. So the square root of this, the square root of this. So U is equals to this, the square root of this, yes. So that will end up giving us the H squared, the partial derivative of H is equals to, this one is equals to this squared. So U squared, because U squared, this one will go away, and then you'll back with it just like that. So it will be U squared del squared H, the 3D wave equation. Now that's for H, the H field. And for the electric field, J scan pia. Okay, it is. I haven't scanned it, but same process. So you'll come. Yes, you'll come here, take this equation, take equation 3, then find the curl of both sides. So when you find the curl on both sides, now instead of you'll find here, instead of h, you'll find the e, which will also tend to 0, is equals to minus the del squared of e is equals to, now here, this will change, because now this will become, what is the number? Okay, cool. It becomes, because now you're going to replace, okay, you're going to replace h. Yes, we're going to get here eventually it comes. In now the other one, you get, looks like this. Like that. Then this one, we already know is equals to here. Is equals to this. So we're going to replace it in this equation, and then we'll end up with del squared E is equals to mu E d E over E t, which is this one multiplied by mu. Yeah. Then its 3D wave equation will be d squared E instead, and then just this, yeah, u squared, del squared, and then E. So the 3D wave equation. So to get velocity in free space, sorry I forgot to scan the last page. Yeah. But to get the velocity, that is here. Get the velocity, we'll have Cu, we found that U, with it? Yes, here. U is equals to 1 over mu E. So in free space, usually U is equals to mu is equals to mu O, and E, the permittivity, is equals to EO. So here, and these are the values for mu O and EO. So you're going to replace them in this equation, and then you get U is equals to 3 times 10 to the power 8, which is what they were asking for in this equation. Yeah. Yeah, that's it. I think I'm done. Are there any questions? Oh, lambda. Thank you, Joseph.
Thank you, Mesh. Whoever is presenting number 7, you can go next.
You can imagine now.
Okay, hi everyone. So I was going through question 7, but first of all, I'd like to hear that you can hear me. Someone please confirm.
Yes.
All right. So let's look at what question 7 was asking. Oh, I'll first present my screen.
Peter, you're breathing in your mic heavily.
Oh. Should be better now.
Absolutely lovely.
Thank you. Okay, tell me if you can see my screen, Jose.
It's coming up now. Yes, it is up.
All right, so let's look at what question 7 was asking. Here it is. A dielectric medium has a dielectric constant of 3. It is found out that the maximum displacement current is equal to the maximum conduction current at a frequency of 4 megahertz. Find the conductivity of the medium. So here we have a couple of things that have been given. Dielectric constant, maximum displacement current, and maximum conduction current. Now, good thing is this is just going to be a build-up from what Mesh has already presented, but these two that we have been given, displacement current and conduction current, we have been told that they were equal in this particular question. So let's first look at what displacement current and conduction current are. Right, so from Ampere's circuital law for static electromagnetic fields, this is not what we are looking at now. We are looking at time varying electromagnetic field. But for Ampere's circuital law for static electromagnetic fields, this here was the formula. The curl of the field intensity was giving us the current density. So from vectors, the divergence of any curl is always 0. So in this particular case, the divergence of our curl, which is the curl of the field intensity, is equals to 0, and it's also it's equal to the divergence of the current density. But for time varying electromagnetic field, we know that the divergence of the current density is not equal to 0. This is from Minakumari. The divergence of the current density for time varying electromagnetic fields cannot be equal to 0. So for us to equate the two, like we were equating them up here, for us to keep equating them, we have to introduce a term. So now this term that we introduce is JD. Now this JD now becomes the displacement current density. So now we have two terms. We have introduced a new term because you want to maintain the equal sign. And we saw that for time varying electromagnetic fields, the divergence of the current density cannot be equal to 0. So it's explained that Maxwell figured that there has to be an extra thing that has to be added. So then they added JD, which is the displacement current density. Yes, so we have JC and JD. JD is displacement current density, and now JC is conduction current density. So from these two, in Minakumari, there's a little bit of derivations that is going on for these two, but they cleanly boil down to these two formulas down here, where the displacement current density is given by the permittivity times the frequency times the electric field intensity. And the conduction current density is given by the conductivity times electric field intensity. For all the questions that are touching on these two, JC and JD, we are going to be using these formulas. I tried to look at all the questions that are in Minakumari, and these are the two essential formulas. So I didn't exactly understand how the derivation was going on, but I figured knowing these formulas is important. Perhaps if someone can understand the derivation, they can explain to us. So we're going to stick with these two derivations for this question. And you can see that when they are equal, like in our question they are, we can cancel out the electric field intensities. So now you remain with the permittivity times the angular frequency will give you the conductivity. So then depending on whichever parameters you're given here, you can always get the other one. So now we can get the angular frequency if we are given the conductivity, and we can get the conductivity if we are given the angular frequency. So up to that point, I guess we are good to tackle on our question. So going back to it, we had been given the permittivity as 3, the relative permittivity, and the frequency as 4 megahertz. And so this is just showing the same formula that I have tried to explain, that the conduction current density is the conductivity times the electric field intensity, and the displacement current density is the angular frequency times the permittivity times the electric field intensity. We know that angular frequency is given by 2 pi f, right? So we have been given the frequency already. So we'll just get the angular frequency and substitute it in the formula. For permittivity, we know that it's permittivity of free space multiplied by the relative permittivity, and E represents the electric field intensity. So if you look at the question, it is found out that the maximum displacement current is equal to the maximum conduction current at a frequency of 4 megahertz. Find the conductivity of the medium. So these two are equal according to the question. So if we equate the formulas that we have found out, again, the electric field intensities can cancel out. So then the conductivity remains to be the angular frequency times the permittivity. So now we just key in the formulas. Angular frequency is 2 pi f. E is given by E naught times ER. And we find it to be the conductivity. We find it to be 6.6. The formula for, the unit for conductivity is Siemens per meter. And that was it for question 7. It was pretty direct. If you want to look at it, it's on page 330. Right from page 330 to around 340 of Minakumari. Yeah, and that was it for question 7. Any questions? Okay, so while going at it, if you find anything, any question, you can feel free to get back to me even later. I'll stop presenting.
Okay, thank you, Mbalo. Oh, who is taking us through question 8?
I'm supposed to take question 8 with Steph. She's supposed to present, but she's not available. So I'll just take over. It's simple enough. Let me just present my screen.
Okay, sir.
Can you guys see my screen?
Yes.
Okay. Question 8. What are the main differences between electric circuits and magnetic circuits in terms of current and flux? So they're given in our notes. It's pretty much straightforward, and the question was asked, just give. So 1 is this first one. This first one. Current flows in an electric circuit while magnetic flux does not. In an electric circuit, you can remember from PE, um, through drift mobility of electrons, it allows for current to flow because current flows in the opposite direction of where electrons flow. I think that's pretty much straightforward and self-explanatory. So the second one was conductivity does not change in current density in electric fields, whereas permeability mu varies with flux density in magnetic circuits. So this is current density, which is just the same as Ohm's law in point form. So it does not change with current density, the conductivity, and in magnetic circuits, it varies. For magnetic circuits, okay, for magnetic circuits, I can give you guys a visual representation just to explain it. Let me just try and draw. You can remember from machines last sem, the BH curve. So this side is supposed to be B, and this side is supposed to be H. So every material has different BH curves. Like for I googled this, like cast iron, its curve looks like this. Then it goes to saturation. This is iron, cast iron. Cast steel looks like this. This is steel, and then this is sheet steel. So as you can see from the graph, all different materials have different BH curves, and permeability is equals to mu is equals to B over H. I don't want to write here because, okay, I'm not writing vizuri, but you can just follow what I'm saying. Permeability is equals to B over H. To also help you explain it, think of it as biashara, like a business. When you open up a business, like it's an investment, and every business is supposed to give returns, ROIs, return on investment. So the more you keep investing in your business, the more you get returns. So we can assume B to be returns, and then H to be investments. So for different materials, now different businesses, you continue putting investment, but it reaches a point that the returns become also different depending on the type of investments you're making in your businesses. So that shows that permeability varies with flux density. Yeah, that's it for my question. Does anyone have a question? Okay, so
Thank you, Nigel.
So I'm doing number 9. Sorry, I'm just trying to present. Okay. Share. Can you go to the screen? Okay, you can see the first paper. Okay. So I'm doing number 9. It says, for an industrial application of a steel material, which is in the form of a toroid of diameter d is equals to 15 centimeters, and a circular cross-section radius of 0.7 centimeter is to be used. The relative permeability of steel is 1000. Given that only a current of 5 amperes can be applied from the workshop, where a flux of 0.2 milliwebers is desired, determine the number of turns of wire that can be used for that design problem. Okay. So let me just open where I did it. So this is, I hope you can see, this is, so a toroid is like, let me call it a pipe in quotes. It's like a pipe that is yenye imekunjwa, yeah, to form this kind of circle. So this is a toroid. And then of course it has conductors or wires that are wound on it like this. So for this question, your knowledge on electrical machines last sem is actually what you'll apply, because it's nothing new really. So in the question, I wrote my values here. We were given that the diameter, the radius of the cross-sectional radius of the toroid is 0.7. So we have your radius. See, sorry. So it's like this radius is 0.7. The diameter of the whole toroid is 15. We have relative permittivity is 1000 and current is 5 amperes. So we want to calculate number of turns that are there in this toroid. So first, if you remember your formula for reluctance, nimekuja nikaandika hapa. It is 1 over mu naught mu r times area. So first, this is length. I hope you don't confuse. So this is length. Length is actually like the circumference of this particular toroid. So if I do circumference, then my length is pi d, and the diameter, so you're using the diameter of the toroid is 15 for you to get your length as this. And then, of course, cross-sectional area, you use this value now to calculate cross-sectional area. So it's pi r squared, yeah. So we've converted to meters. So this is your cross-sectional area. So you have length, you have area. We know mu naught, mu r tumeambiwa ni 1000. So if we calculate for r, you just come and substitute your value of r. Yes?
Celestine, could you
Oh,
please
you guys
zoom
can't
in?
see. Poleni, wa pole.
It's
It's better. Okay.
Hmm.
So I already calculated length, cross-sectional area, and then now I'm substituting, because I said r is L over mu naught mu r times A. Yeah. So of course we know mu naught is 1000. So when you substitute your L here, your mu naught, your mu r, and your area. So this is what you get for r. And then you can use this relation. You know, force is equals to, so this is magnetomotive force is equals to Ni, which is also equal to phi r. This phi r, penye natoka, you remember when you say force is analogous to voltage. So from Ohm's law, we know V is equals to I R. And then we normally say that magnetomotive force is analogous to voltage, flux is analogous to current, and resistance is analogous to reluctance. Let me just call it R. So yeah, this is where you're getting this formula for force. And then, yeah, making in the subject, we were given flux as 0.2 milliwebers. We already calculated reluctance. We were given current as 5. So you get your number of turns as 97.4. So I hope that's comprehensive enough for you guys. Does anyone have a question? Okay. Okay. Sawa. Sawa. Aya, I'm done.
Wait, Celestine, I have a question about the number of turns.
About the number of turns. Mhm.
Yeah, the way if so we've gotten 97.4. Should you, because that's a fraction, should it be 98? A number of turns.
I didn't really think about that, but I think you can round it off upwards, but I'm not sure. I have not done research on that, because when we did it in class, we got a decimal and the lecturer didn't really mention whether we round it or we leave it there.
Oh, okay.
Yeah.
Okay. Thanks.
Okay.
Thank you. Oh, okay. So I think we agreed that number 10 we'd all try and then discuss on the group. Was anyone able to do it? We still try and do it later on and then we discuss baadaye kwa group chat. Still try. Okay. Okay. So I'll stop recording. But then we need to discuss about what